Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, I will present you another example of the method of distribution functions. Let's begin. So, the problem that I would like to solve with you is this. We have a standard normal distribution, meaning that the random variable z has, is normally distributed with mean 0 and variance 1. Okay? Now, we're going to be transforming this original random variable z. We're going to be squaring it, and we're going to be labeling that transformation as u. Okay? That's our new random variable. So, what we would like to do is finding the probability distribution of u. It happens that in this case, that transformation is one member of a famous probability distribution family, the gamma distribution family. Well, before we proceed, let me remind you what's the main idea behind the method of distribution functions. The main idea behind this method is exploiting the relationship that there is between the CDF, the cumulative distribution function, and the PDF, the probability density function. Okay? So, if we take the derivative of the CDF, the cumulative distribution function, we obtain the PDF. Okay? So, what we're going to be doing here is trying to find the CDF of u, right? And then take the derivative. And the thing is that we have information about the distribution of the original random variable c. So what we will try to do, right, is expressing the CDF of the new random variable u in terms of the old random variable z. Okay? Okay, here we go. Let me walk you through this. First, note, right, that the support for a normal 0, 1 is from negative infinity to infinity. So if we square a real number, right, the result will be either 0 or positive. Okay? So the possible values for our new random variable u are just positive numbers or 0. Okay? So the non-zero part of our PDF will be just for values that are positive or 0. Okay? So if we wanted the probability that c squared was less than or equal to, say, -3, the probability of that happening would be 0. Okay? So the CDF, the cumulative distribution of u for negative values, is going to be 0. Okay? So case number 1, case 1, the CDF, right, of our new random variable u, which is the probability that the random variable uppercase u is less than or equal to some number, is going to be 0 if, right, if u is negative. Okay, so we have that one there. Okay, okay, and we're going to slightly modify that in just a minute. Okay, but we have the first case done. Okay, Now, let's do the second case when u is greater than 0. Okay, so again we apply the definition basically of CDF. This in terms of a probability is the probability of the following event, that the random variable u is less than or equal to a number u. Okay, then we use the fact that u was defined as the square of z. Okay, so the event u, the random variable u being less than or equal to some number, is equivalent to c squared being less than or equal to that same number. Okay, now the probability that z squared is less than or equal to u is equivalent to this event, the probability that z is between negative square root of u and positive square root of u. And to give you some intuition behind that, to see it graphically, I prepared something for you. I prepared a graph. So here's z, here's your transformation u, which is c squared, is a beautiful parabola, right? And then we see that if, say for instance, we had 100 here, right? If c squared is going to be less than or equal to 100, then z, the original random variable, has to be between negative 10 and 10, which is negative square root of 100 and positive square root of 100. Make sense? Okay. So, but that we could express this probability in terms of the CDF of z. Again, note how we are trying to express the CDF of u in terms of the CDF of z, because we have information about the original random variable. We know that z has a normal distribution in this case, so we're trying to exploit to use that information. Okay, now, so what we have established here is that the CDF of u equals the CDF of z evaluated at the square root of u minus the CDF of z evaluated at negative square root of u. Okay, so now we take the derivative with respect to u, okay, on both sides, and the derivative of the CDF of u is going to be the PDF of u. We are taking the derivative on the right hand side, and then we apply the chain rule. The derivative of this guy, of the CDF of z, is going to be the PDF of z, right, evaluated at the square root of u, times the derivative of the square root of u. Okay, that's what we have here. Then we take the derivative of this second term, so we have just the derivative of minus the CDF. It's going to be minus 1 the PDF of z evaluated at minus the square root of u times, applying the chain rule, the derivative of minus square root of u. But then what we end up with, right, is going to be minus 1/2 u to the negative 1/2, right? So we just do the math, minus times minus, and then we have this. Okay, make sense? This just is a result. This guy, 1 over the square root of 2 times square root of u, is just a result of applying the chain rule. Okay? Okay. Now, this here, what I have here is the PDF of a normal 0, 1. Okay? If you don't remember that expression, let me remind you that on page 838 of our textbook, we have that beautiful table of expressions for the PDFs, means, variances, and MGFs of popular distribution functions. In the case of a normal, it looks like this. Since we have a normal 0, 1, where we have a sigma, we just put a 1. Where we have a mu, we just put a 0, right? So we end up with just 1 over the square root of 2 pi e to the negative 1/2 z squared in our case. Okay, so that's what we have here. Then we just have to plug in, right? We are, let me remind you, evaluating that expression at the square root of u. Okay, so wherever we have c here, we are going to be putting a square root of u. So square root of u squared, it's going to be just u, right? In the case of this one, that minus, when we square, is going to turn into a plus. So that's why we have this. Now these two terms are identical, right? So we have 2 times this expression. The 2 will cancel out. Okay. And yeah, so the 2 will cancel out. And also when we have this, right, when we do the math, right, we are going to have that this coefficient here becomes 1 over the square root of pi times the square root of 2. Okay, just after simplifying that coefficient here. Okay. Now, here, this guy here, the square root of u, right, 1 over the square root of u, we are re-expressing as u to the power negative 1/2. Okay, why we are doing that? Here, let's go back to our table. Okay, we have u to some power e to the negative u divided by a number, a constant. If you take a look at that, you should go, oh, I've seen something like that before. That kind of looks like a gamma, right? So if you go back here to your table, yeah, it looks like a gamma, right? So y to the alpha minus 1 e to the negative y divided by beta, and then we have this constant that is related to the gamma function, right? Okay, so now let me be super specific here, and let's re-express the PDF that we're seeing here. Okay, so for case 2, after we did the math, u greater than 0, after we did the math, we ended up with f of random variable u evaluated at u, right, it was going to be, well, was 1 over gamma function there, right? The gamma function evaluated at 1/2 times 2 to the power 1/2, and we have u to the power 1/2 minus 1 times e to the negative u divided by 2, right? So can you see that this guy is identical to what we have here? E to the negative 1/2, right, is the same as u to the 1/2 minus 1. The other one is exactly the same. And here we have 2 to the power 1/2, which is just the square root of 2, right? And now gamma evaluated at 1/2. Well, we can show that the gamma function evaluated at 1/2 equals the square root of pi. I'm not going to be discussing this with you here, but if you go to the appendix of our lecture notes, you'll see a proof of that. Okay, so if you have time, take a look at it later today. Okay, but there it is. Okay. So basically, after we did the math here, what we end up with, right, is that this guy u has a gamma distribution with parameters alpha equal to 1/2 and beta equal to 2, right? Okay, nice. Something else that I want you to remember from what we did back in chapter 4 is this: the definition of a chi-square distribution. So a chi-square is a particular case of a gamma, okay? And what we have for that particular case is that beta is equal to 2, and then the parameter alpha is going to be expressed as another number, nu, divided by 2. And nu represents the degrees of freedom for the chi-square distribution. Okay, so in this case, beta equals 2, right? And alpha is 1 over the square root of 2, right? So that means that nu, the parameter of the chi-square, is just 1, just by the very definition of a chi-square. Okay, so what we have here is that our new random variable, which was normal 0, 1, and then we square it, has a gamma distribution. In general, it's a member of the gamma distribution family with alpha equals 1/2 and beta equals 2. But in particular, right, you can refer to that guy as a chi-square with 1 degree of freedom. Okay? Make sense? So again, let's summarize what we just did and what the method of distribution functions is about. Okay? So what we do here using the method of distribution functions is exploiting the relationship between the CDF and the PDF. If you take the derivative of the CDF, you will have the PDF. Okay? And then what we do is just use this definition, the definition of the CDF in terms of an event, right? So the random variable being less than or equal to some number, right? We have to take into account both cases, meaning when u is less than or equal to 0 in this case, because in general we have to define the CDF over the entire real line. Okay, so let me just say one more thing about this. Remember that the CDF must be right continuous, and since in the case of a continuous random variable the inclusion of a point doesn't change the probability, we could have this here. For u less than or equal to 0, we have that the PDF will be 0. And when u is greater than 0, we have this particular case. So the square of a normal 0, 1 is a gamma with parameters alpha equals 1/2, beta equals 2, but that is a particular case of a chi-square distribution with 1 degree of freedom. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.